It's an expression that contains a square root in it. So if you've seen the square root symbol, okay, that's a radical expression, one that involves a square root. So we'll be writing, these all have radicals over them. We'll be writing these in simplified radical form today. And then the other thing that shows up when you're talking about special right triangles in geometry is rationalizing the denominator. The denominator is the bottom of a fraction. And so the goal will be to remove any radicals that you have at the bottom. This is kind of wordy. I would just say removing a radical as a denominator. You could stop right there. And I'll show you the process of what we do to rationalize the denominator, hopefully today. And then tomorrow can just be a work day. Practicing. So there's something called the fundamental theorem of arithmetic. Did you guys talk about this last year? Like, did you guys fundamental theorem of arithmetic? Here's what it says. Maybe you did talk about it. You didn't call it that. But it just says that any whole number like 48 can be broken down into a bunch of prime numbers multiplied together. You should talk. Okay, that's the fundamental theorem. You just probably didn't want to use that term. But so that's what we're going to do with 48. And what we're looking for are groups of 2, and I'll show you why in just a minute. So take the number 48. What's the first set of factors that you think of? You think of 48?
6 and 8.
6 and 8 is the first one. Okay. So if we have 6 and 8 here, and then we keep going. So 6 breaks down as
2
and 3, right? And then 8 would be
2 and 4.
2 and 4, and then we can take 4 a little further to 2 and 2. Now, what we need to understand is that there's a radical over the top of this, so there's got to be a radical over each of these as we go through. We don't write the radicals when we're doing the factor trees. You don't need to do this, but you need to understand that there's a radical over each of these. So I'd like you maybe just to do this on this first one. And so what we're looking for, this is a factor tree. We're looking at the roots. You know how roots grow into the ground? They're not all even necessarily, right? But at the very bottom, if you think of the very bottom of each root here, we've got a number. So we've got root 2, and then we've got another one, root 3, and then another root 2, and then root 2, and then root 2. So do you see all of them here? 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, right? So what we're looking for, well, first of all, we should verify that this actually equals 48, does it? 2 times 3 is 6, times 2 more is 12, right? Times 2 more is 24, times 2 more is 48. So it does equal 48. Do you see any pairs in here? A couple sets of pairs, right? These two are a pair, and these two are a pair. And anytime you have a pair, here's what it looks like. Square root of 2 squared, that's what this would be. And what happens to the square root when you square it? It does go away. So this would just equal 2. So every time you have a pair, you have a perfect square. So root 2 times root 2 is just 2. Okay, so root, I'm going to sneeze. Root 2 times root 2 is 2. And then here we have a root 2 times root 2, which is just 2. And then I have this times root 3 here. So I've got a 2 times 2 and a root 3, which simplifies as 4 root 2. And that's your final answer. That's simplified radical form.
What is it? Root 2.
It's not 4 root 2. It's 4 root 3. Thank you, Jenny. We got the 4 by taking 2 times 2, and the 3 is what's left over. And if there were other things under radicals that didn't have a pair, we would multiply them all together. Okay? Have you guys seen this before? Have you done it? Nobody? No. Did you guys do this last year? Okay, you may not have done it. All right. Square root of 32. How would you break that up? Maybe as first factors that come to mind. 8 and 4. Okay. I want to show you something with this. And then 8 would be 2 and 4, right? Now, you don't have to break it all the way down into its primes. As soon as you see a pair, you have a perfect square. So do you see a pair up here? Pair of fours, yeah. And so that pair of fours, I just pull it out. So I have a 4 outside times the square root of what? What's left over without a pair? 2, and you're done. That's it. So you don't have to break it all the way down to the primes. As soon as you see a pair, then you can take one of those from the pair out of the radical. Does that make sense? As soon as you see a pair, you can take one of these out. Since there isn't a pair of 2s, I have to leave the 2 under the radical. All right. What about the 63x to the third here? What are the first factors that come to mind on that? Yeah, probably 7 and 9. Okay. So we've got 7 and 9. And then we've got 1, 2, 3 x's. Okay, so 3 x's there. So you see any pairs yet? Yeah, I see a pair of x's. So we can pull an x out. Can you see any pairs here? Any other pairs? Okay, but we can take the 9 and write it as 3 times 3, right? So I do have another pair there. So my two things that I have pairs of are 3's and x's. So those both come out of the radical. So I have 3x. And then what stays under the radical? This is a little tricky here. You gotta. An x does, yeah. You're just looking at the bottom of the roots here, which is always tricky because they're not all at the same level.
Oh, 7.
And then there's a 7 there, yeah. And so why not the 9? How come I'm not pulling the 9 in? Yeah, it's not at the bottom. We already dealt with it, yeah, with the 3's. So that's simplified radical form with variables, okay? So any questions on that? First and 10-2. All right. So moving along here. I should say on these, you should always check to see if you have a perfect square first, but I'm going to show you one other method here. Erase these, just start over again. In my trig class, the students in there use this stuff, do so much of this simplifying radicals that they would have their perfect squares memorized, probably through 15. I don't know if you guys have done that before, but here's what I mean by perfect squares. I'm going to start with 2 squared because 1 goes into everything, so that doesn't really help us. But 2 squared is 4, 3 squared is 9, 4 squared is 16. Do you guys know your perfect squares up through 100? No? 64, 9 squared is 81. It'd be helpful to know them up through 15 here. You know what 11 squared is? 121. And then 12 squared is 144. 13 squared, 169. You know 14 squared?
196.
Yeah, it's 196. And then 15 squared is 225. Yeah. It's probably helpful to know that for using this method. And if this method doesn't work for you, you can always use a factor tree. So right here on 160, what I would do is I would start up here with the 4. Does 4 go into 160? Can I divide 4 into 160 and get a whole number? That goes in 4 times. Yeah, so that works. The question is this the biggest perfect square, or is there something in this list that's larger than 4 that would go into that? We're trying to find the biggest perfect square and then remove it out. And then we can do these in 2 steps. I think I saw some of you doing that. Somebody's shown a couple of you this before. 16 is bigger, yeah. So 16 goes into 160 10 times. So what we can do over here is rewrite 160 as square root of 16 times square root of 10. And when we look at 10, a lot of students think, well, can't that be broken down more? Yes, it can be. But here's the deal. 10 is equal to 2 times 5, and neither 2 nor 5 are perfect squares. Like there's no pairs within the factors of 10. There's no pairs. So 16 times 10, 16 is the biggest perfect square that goes into it. And the square root of 16 is 4, and so we just write this as 4 root 10. And that's it. So if you can find the biggest perfect square from that list, as long as the numbers aren't too big, once you get to more than double of 225, so more than 450, then you might need to use the factor tree if it's over 450, unless you know your perfect square is all the way up to 20 squared. You guys know 16 squared and 17 squared, 18 squared, 19 squared? Maybe not. Anyways, if you don't know those, then this method won't work beyond twice 225 or 450. Okay. What about this one, 64 over 49? Is there a perfect square that goes into 64? 8. Jonah, which method do you use? Do you use factor trees, or do you just find the biggest perfect square? You do that? Okay. So 8 over, this would be over 7. You just take the square root of each. So on 72, 72 is a really good example. Like 4 will go into 72, but is that the biggest thing that goes into it? I don't think so, right? What about 9? 9 goes into it 8 times, but is that the biggest one? I don't think so. So we keep going down the line, right? Here's how I know that 9 is not the biggest one. If I do 9 into 72, I get 8, right? And the thing with 8 is that 8 is made up of a perfect square, 4, and 2. So if when I divide one of these perfect squares into that number and you get another number that's smaller but has other perfect squares in it, then you didn't find the biggest perfect square. Yeah, that's how it works. As a matter of fact, if you took what's left over here, here's 9, and then we have times 8 can be thought of as 9 times 4 times 2. Both of these are perfect squares, and when you multiply them together, you get the actual biggest perfect square, which is 36. 36 is the biggest perfect square that goes into 72, and it goes in 2 times. So you have square root of 36 times square root of 2, or 6 root 2. So that's the biggest perfect square factor. Right. So if you can use that method, if you're good with your perfect squares, and you can even use your calculator. You just start trying 4 into the number, 9, 16, 25. And the question is, what do you have to go up to? Like, when could you stop? Like with 72, as I'm going down the line, if I went to 49, right? 49 does not go into 72, and also 49 is already more than halfway to 72. As soon as you're over halfway to that number, you don't need to keep trying it. Does that make sense? Like, you don't need it, because 2 is the smallest prime factor that's going to work. 2 is so once you're over halfway there, you can stop. All right, we're going to talk a little bit about removing variables a little bit more. 54x to the 7th. Can you think of the biggest perfect square that goes into 54? 4 doesn't, right? 4 doesn't go into it. Does 9 go into 54? Yeah. What about 16? Will 16 go into 54? 25? No. 36? No. And then I can stop at 36, because 36 is already more than halfway. 54. So 9 is the biggest one. And here's the deal on this. 9 is the biggest one when it comes to numbers. If you think back to when I wrote, if I were to write 7 x's out, how many pairs of x's would I have? If I wrote 7 x's out, I can do it if you want to see it. 3 pairs, right? So that's the way it works for variables, is that the perfect square, the biggest perfect square that goes into x to the 7th would be x to the 6th, which would represent 3 pairs. And then what's left over here? So I have 9x to the 6th times 9 times what is 54? 6, and then x to the 6th times what would be x to the 7th? Like how many, what's the power on x that goes here? Just 1. So just verify that this, if I multiplied it together, would equal 54x to the 7th, right? So what's the square root of 9x to the 6th? Remember how many pairs of x's there'd be. So square root of 9 is 3, right? And then square root of x to the 6th would be x to the 3rd, yes, because there are 3 pairs. And so what you do to take the square root of a power, you might want to write this down, of an even power is half that power. So you just list the biggest even power you can that goes into that, and then take half of it. All right, sometimes you can simplify first before doing what we did here. Like 8 and 50 are both even numbers. We could cut them in half. So you would have square root of 4 over 25. And then when it comes to the x to the 3rd over x to the 1st, this goes back to chapter 7. When you're dividing x's, what do you do with the powers? You remember, Adam? So if I put a little 1 on this one, what would you do with the x to the 3rd and x to the 1? What would you do with their powers? You guys remember? Anybody? Let me ask you in a different way. How many more x's are there up here than there are down here? 2 more. You subtract them, yeah. So it's x to the 2nd is up here. And so the way we think about this is equal to square root of 4x to the 2nd over square root of 25. It's okay to rewrite the square root twice. That's what that big square root over the whole thing means. And then the square root of 4x squared is 2x, and the square root of 25 is 5. You're done. All right, then now you try. It's too different for you just to try. I'm going to show you something. They threw something out here that they don't have out there. So there's a negative m out here. What do we do with this negative m? We just kind of bring it along for the ride here. It's going to get multiplied by whatever we pull out. So what's the biggest perfect square that goes into 80? Let's put it on our list. Is 4 going to 80? Does. It goes 20 times, so keep that in mind. 9 doesn't go into 80. Does 16 go into 80? You try it real quick. What's 80 divided by 16 if you get a whole number and it goes in? You know, 80 divided by 16? 5, yeah. So 16 is bigger. Does 25 go into 80? No. 36 into 80? No. So look, I think 16 is the biggest, right? So I'm going to rewrite this as 16, and then what's the biggest perfect square that goes into m to the 9th? In other words, what's the biggest even number that's less than 9? The biggest even number that's less than 9. Yeah, then you go a little bit bigger. 8, yeah. So m to the 8th. And then we've got times whatever is left over. You said 16 went into 85 times. And then I'm always going to have, if there's an odd number under the radical, an odd power, you're always going to have a single letter left over, okay, every time. So we've got negative m times square root of 16m to the 8th is 4m to the 4th. And then I can't touch the square root of 5m. Have you guys heard the jailbreak metaphor for square root, simplifying square roots? Have you heard that one? The jailbreak? No? Nobody? Really? You know how I said if there's a pair, there's a perfect square? Well, the jailbreak analogy is if there's a pair, they get out of jail. They help each other get out of jail. And if they don't have a buddy, they can't get out of jail. If there's a pair, out of jail. So m to the 8th, 4 of them can get out because there's 4 pairs there. So negative 4m to the 5th square root of 5m. All right. Any questions on this? All right, multiplying 2 radicals. So there's 2 different ways to approach this. One way on this is to multiply these together so that it looks like what we were just doing. But that's kind of counterintuitive because if I multiply them together, I'm going to get a bigger number, and I'm trying to break it down, right? So to multiply them together kind of doesn't make sense. Here's probably the way that I would approach this. The 2 and the 3 can already be multiplied together. They're outside of jail, if you were outside of the radicals. So this is 6. And then I have square root of 7x. I'm just going to leave it. And then how does the 14 break down here? Yeah, 7 and 2. And so I have square root of 7 times square root of 2 times square root of x squared. Okay. You kind of break it down in that way. And so looking at that, do you see any pairs in here? I should really do one more step here. Let me do this first. Square root of 7 and square root of x times square root of 7 times square root of 2. What's square root of x squared equal? It's just x, so it comes out. So as you're looking at this list of factors, that's what it is. This is like a factor tree method is back again. What pairs do you see, or what pair do you see? There's one pair. Well, this doesn't count as a pair because they don't both have a square root over them. But 7 is a pair, so 7 will come out. I'll bring the x over here, and then I have the x and the 2 is just left over. So my final answer is 42x square root of 2x. So 42x square root of 2x. That's kind of a hard one to start with, but on the Now You Try, they start a little easier. So 18. So here's the deal. I'm going to rewrite this. Just put the square root of 6 there. Square root of 18 could be rewritten as, if you think of a pair, something that would, you could a 9 and a 2. I was thinking, can you think of factors of 18 that would have a 6 in it? Yeah, 3 and 6. So then we have a pair right away, right? So here's my pair of 6s, both under a radical, so I can bring one of them out. So I've got 3 times 6 times root 3, or 18 root 3, and we're done. So yes, you could multiply these together. You could say this is equivalent to 3 times 60 and 48 would be 108, but then you've got to break down the 108, and so it's kind of counterproductive, right? If it's already in form of 18 and 6, I'm farther along down my factor tree already. So when you have multiple radicals that you're dealing with, I would just keep breaking it down. Don't multiply them back together. You can, but I wouldn't. Right here, we have square root of 2 times square root of a times square root of 9 is a perfect square. Let's break this up as square root of 9a squared. That's a perfect square. That's the biggest perfect square that goes into that. And then I have a square root of a left over. Just to show you here, these two together equal 9a to the third. I'm just breaking it up as a perfect square times something that's not a perfect square. So square root of 2, got to leave that alone. You see the pair of square roots of a there. So 1a will come out because of that. And then square root of 9a squared, what does that equal? It's 3a, yeah. So your final answer is 3a squared root 2. This next one's kind of interesting. It actually works out better to multiply them together. Here's why. Maybe you'll see it here. Look at what's under the radical. If you multiply just what's under the radical together, what kind of term do you get? What kind of number? What do you get for the number when you multiply this? You see one of these popping out when you multiply? 5 and the 20, if you multiply those together, you get 100, which is a perfect square. And if you multiply x to the first and x to the fifth together, you get x to the sixth, which is also a perfect square. You with me? So in this case, it's actually better. 7 times 3 is 21. It's actually better to multiply these together. If you can kind of just look at it and see if what I multiply together, if what I multiply together here makes a perfect square, that's probably a better idea on this. So that would be 100 x to the sixth. And so the square root of 100 is 10. I got 21 times 10x to the third, or 210 x to the third. And then this gets us to what I had talked about last chapter, right? This is the quadratic formula. So this is a good review, quadratic formula, for those of you who have to take the test. Are you going to come to lunch and take it? So quadratic formula says x equals negative b plus or minus square root b squared minus 4ac all over 2a. So if I plug in, here's my a is 1, b is negative 6, and c is negative 4. I'm going to plug in to this formula. Opposite of negative 6, which is positive 6, plus or minus the square root of b squared, so negative 6 squared minus 4 times 1 times negative 4, all over 2 times 1. So I'm plugging in a, b, and c to that formula. And I'm going to show you how we can simplify radicals using the quadratic formula. So I had to just leave it last chapter. You just left it after we did the part under the radical. So we have x equals 6 plus or minus. This is 36 minus a negative 16, or 36 plus 16, which gives me 52 over 2. And I had you just stop there, right? Last chapter, you just stop, unless 52 is a perfect square. 52 is not a perfect square, but 52 can be simplified. If you take square root of 52, write it over here to the side. Square root of 52 is equal to what? What's the biggest perfect square that goes into 52? So yeah, 4 does go into it. 4 will go into it 13 times. Does 9 go into 52? 16 go into 52? No, because 3 times would be 48. 25 doesn't go into 52, nor does 36. So it looks like 4 is the biggest perfect square that goes into 52. Square root of 4 times square root of 13, which is 2 times the square root of 13. So what I'm going to do is rewrite square root of 52 as 2 times the square root of 13. So we just rewrite 52 as 2 times the square root of 13. Can you guys tell me what the greatest common factor of 6 and 2 root 13 would be? What's the greatest common factor between these two? In other words, what's a number that goes into both 6 and into 2? 2. So I can pull out a 2. If I divide 6 by 2, I get 3. 2 divided by 2 would just be 1, but I still have that root 13 I have to attach, and it's all over 2. So if I factor out a 2, that's what I'm left with. And then what's 2 divided by 2 equal? Just 1, right? So they canceled equal 1. So my final answer is x equals 3 plus or minus the square root of 13, which is what I would have gotten if I'd done completing the square. That's the cool thing about completing the square, is that you don't end up having to factor in the end like you do with the quadratic formula. because of that 2 times a on the bottom, and then also this 4 times AC here, all this stuff on the top. Sometimes with the quadratic formula, you get some multiple of the simplified version of the answer. So, so now we can actually take the quadratic formula and write it in exact form rather than decimal form or leaving it alone. Okay. One more thing I want to show you here, and then we'll start on the classwork, and we'll have to finish the classwork tomorrow. But this is called rationalizing the denominator. And what it means literally is make the denominator, put it in ratio form here. That's not what I want. Great, lost my page here. I put an undo here. Okay, so we're going to put it in ratio form here. And the way we go about doing that is we just multiply the top and bottom by square root of whatever the bottom is. So you just match the bottom. Root 7 over root 7, because root 7 over root 7 is just equal to 1. So I'm not changing the value of it, I'm just simplifying it. Okay, that's it. I can multiply anything I want by 1. And here's how it works. Root 3 times root 7 is root 21. And root 7 times root 7 is just 7. Because the square roots cancel out. And that's it. Based on that example, can you tell me what I need to multiply top and bottom of the second one by to get that square root of 8x to go, the square root sign to go away? Yeah, square root of 8x. That's it. You just multiply. And so we have square root of 56x on the top. And what's going to happen on the bottom based on my example? First example there. It's going to be 8x. That's it. That's it. That's all you do.
So just times by the.
You do. And that makes it into a ratio in the denominator. In other words, it's no longer a square root. And that's something that will show up in geometry and trigonometry as you're doing it. Like here, I would just multiply by root 3 over root 3. And my new answer would be root 6 over 3. And this one, even when it's written like this, which they do on some of them, you just think of it like this. Root 7x over root 3. So what would you multiply top and bottom by here? Yeah, so go ahead and do that. Multiply by root 3 over root 3. Square root of 21x over 3. So it's not real exciting stuff here. Pythagorean theorem is much more interesting. But as you're doing the Pythagorean theorem or the quadratic formula, you're going to be asked to write it in simplified radical form. So you need to know how to do this. Okay, in geometry, will be a lot of this, and in trigonometry. So, I have the learning target up here. So some version of that for your summary. And I'm going to wait. I have your pink sheet, so I'm going to wait till we finish. I just assigned one. I don't know that you're going to make it through 1 through 17 on it, but eventually we're going to do 1 through 25i. That's what it says on the pink sheet from your classwork. So let's see if you can just get as much done as possible in the next 15 minutes. At least try to get through, I think it was number 9. It's that first top section there. So and Jonah can help you out. But they could at least get through 1 through 9 on it. And then we'll finish the rest tomorrow. Here's your homework. You're just going to do, the homework says TBA on there. So we're not getting into the bookwork yet. I just want you to do the front page of this. And there's some extra notes on here. I think it's a helpful page. It's something we use with our geometry classes to review what we are doing this year. So hopefully this is helpful. It has some notes on it about some of the stuff we did today. Some of the rules of radicals. So we're not getting into the book stuff yet. So we're on, the homework is just 1 through 8 on this. Just do 1 through 8 and then I'll give you the full credit tomorrow. Just 1 through 8. And right now in the classwork, if you can just get 1 through 9 odd, then that's great. And like I said, Jonah or I can help you. Be sure to write your summary up here so you have it tomorrow when I go to check it. I'm not going to check it until tomorrow. Check all the notes.